And howdy.
Howdy.
Any questions on the homework? Can we do the gear?
Yes.
What?
Like the whole gear? Can we just make it? Okay. So the gear is referring to one of the problems on homework 4, and that would be the search box. Homework 4 asks you to draw a gear. This is supposed to give you practice with creating patterns, and this is the sort of thing that is easier to start with a pattern on a sketch. So what I would recommend doing here is drawing an arc with a line with an arc with a line with an arc. You can also get there. Here, ignore the assembly that's about to appear. We'll get to that in a second. So if you were to draw this as a circle, and then another slightly more different circle, and then the gear starts at the top middle. So I'm going to draw a couple of lines like here, and also like here, and then I'm going to draw some construction lines with which to trim, and I have the makings of a gear tooth, like this. I'm going to verify that my two construction lines still are coincident with the origin. I am going to add some fillets to make this more roundy, like this. We have radii given there. They are all 0.05, 0.05. The outer diameter is 1.75 in radius. So I can add a radius to this. That'd be 1.75? 75? Nope, that's not right. Let's try that again. 1.7, nope, decimal key. Okay. 1.75. That is also great. I like this. This is good. I like the way that this gear is really mechanical. It's really good in its goodness. Okay. So what I'm going to do here is get rid of all the dimensions that I've established. I'm going to try reapplying a dimension to the top one here and seeing if that breaks it again. See, whatever your first dimension applied is, Solidworks scales your sketch to that. So pro tip. If you make your sketch way too big like I did, and then try to apply a sketch dimension that resizes everything, it's going to break all your geometry. Okay, so we have here the beginnings of a gear because we have one tooth to pattern. I'm going to pattern that by creating 21 of them, and I will add a couple of extra relationships here just to try to make sure that when I start patterning it, I'm not breaking as many things as possible. So relations to pin down the location of the tooth in a left to right dimension. I pin down the radii so that they start and stop at the same point so they can't shift off. I'm going to make these equal length. And that's fun. Okay. So I think that I have enough here to start the process of patterning it. So I'm going to select these. Nope. Select that, control click, 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 control click. Then I'm going to hit circular pattern. I want 21 of these instances. It's going to assume that I want to pattern around the origin, which is great. Well done, Solidworks. I'm going to click OK. And then I'm going to join together the ends of these lines, because you'll remember one of the big advantages of a pattern within a sketch is that your sketched entity that you use to pattern can reference the patterns. Real convenient. Now, I assume that somewhere on here I had a dimension to, yep, okay, 0.05 is the distance between half of the gap tooth and then the corner where that would intersect, so 0.075. Let's see if I can't remember that. Whew, man, that's inconvenient. I've already created a fillet. So I will add in a point. I'm going to tell SolidWorks, hey, that point should be at the intersection of that line and also this arc right there. And then I'm going to apply a dimension. That dimension should be, nope, 0.05, nope, 0.075, much more better. And then I will add an equal relation, and that should, why did you break? Oh, right, because you're an arc, so I need equal curve length. There we go. I can tell that not everything is fully defined because these haven't turned black yet. So I will start the time-honored tradition of just grabbing stuff and dragging around to see what's not fully defined. I see that I don't have a tooth depth defined, so I should add that in. That'll be 0.15 across, and then got to do the same intersect nonsense. So point and point. Control click, and then control click, and then control click, and control click. Now I can apply a dimension from these two sketch points. That was 0.15 question mark. Okay, lastly but not leastly, do we have a depth of the tooth? We do not. So we do have 0.25 indicated here, and we are told that that is a typical dimension, meaning anything that looks like it's 0.25 is going to be 0.25. So this distance here is 0.25, this distance here is 0.25, this distance here is 0.25, and this distance here is 0.25. So I will add in an offset between these two radii, see if the potato can display it. You can do it. I believe in you. 0.25, and now we have a fully defined sketch. So at this point, I could create a linear extrusion, cut out the holes, or I could draw in the holes and cut them as part of the same extrusion. So I figure, just to demonstrate the power of the sketch pattern and to try to overwhelm my computer's ability to show more than 3 entities in the same sketch at the same time, I'm going to draw out the inner hole and the cutouts all within the same sketch. So I'm going to draw some arbitrary lines here because it doesn't really matter where this is positioned yet. I'm going to purposely ignore all of SolidWorks like, hey, do you want this to be related to, oh, no. Do you want this to be related to that? No, I don't. Come on, computer, you can do this. Click on the origin, click on the line, make that coincident. Click on the origin, control click the line, make that coincident, and then trim and trim. So this inner circle had a diameter of 0.5, there was an offset here of 0.25, and then there was an offset here of 0.25. I guess that's not necessary. This one would be 0.25, and then I can start the process of, ooh, I should fillet this first. Let's fillet it before we pattern it. All 0.125 again, so fillet on this, and a fillet on this, and a fillet on this, and a fillet on that, and then 0.125, 0.125, except select the entities that I want to pattern. So that's the inside of this, fillet, line, fillet, arc, fillet, line, and arc. Go up to circular pattern. It'll assume the origin. Once again, spot on, way to assume things, SolidWorks. So now I have 7 holes. I can get them positioned so that my 2 lines are positioned around the origin. To do that, one way to do the same relationship would be to apply horizontal between these top 2, which will make sure that those are offset. I guess these can't really be parallel and also coincident with the origin, because then they'd be on top of each other. I really prefer that they be parallel because that's what the drawing gives me. Shows parallel because those are supposed to be straight lines. So I got to go back into the entity for which I established the coincident relationship, delete it for both of them, and because it's patterned, that'll delete the relationships on all the others. Now I can apply a parallel relationship. That's looking better. Once I apply a smart dimension between the 2 lines of 0.25, because typical. There we go. Now we are almost there If I click and drag to see what's not fully defined, oh yeah, I broke that because I got rid of the coincident. So if that's vertical, then everything should be fully dimensioned. And look, everything except for this blue dot. Blue dot? Why? Oh, I like the way that I grabbed that and dragged it, and it became fully dimensioned on the other side. That's fun. Well, that should be tangent, which it is. This should be tangent, which it is. SolidWorks, this point is totally fully defined. Why are you saying it's not? No, I'm not taking that. There's a better way. Yeah. Ha! I fixed it, and I didn't even fix it. In your face, SolidWorks. I could have, but that would have been the easy way out. Okay, now that I have the entire sketch, I can fully define and then extrude. This is, what's the thickness of the gear? 0.25? Okie doke, 0.25. And mid-plane. Boom. And then gone forever. Other questions?
Do we get docked if like we have it oriented the wrong way? Like say we have the Y pointing up and the Z and X pointing to the sides?
You do not get docked unless the problem statement has clearly defined front, top, and right projections. In that case, you do.
Like the bishop?
Like the bishop. That does have established front, top, and right projections. So you have to follow that. The questions? Okay, the topic of today's class is assemblies. Assemblies are the combination of parts together. And when I tried to come up with a good example for the sort of thing that you would model as an assembly in SolidWorks, instead of doing the chair thing again, where I talk about the legs and the bottom and the top of the chair, I thought I'd use a real example. And as this is apparently the cat paraphernalia class, this is a pet feeder that I designed and printed and used for a while, and then it got replaced. This is the Mark II design. There's now a Mark III that fixed some of the mistakes that, opportunities for improvement that existed in the Mark II. So, this cat feeder is entirely 3D printed except for this part. This is just a Walmart food storage container that I cut the bottom off with a bandsaw, very not neatly, because it doesn't matter, because it's nested into other parts. But the actual 3D parts in this consist of separate entities like this. So this is the food funnel, takes it from the container down into an auger. That auger runs, drops the tube off the front, and then nests inside of this assembly. So there's a front and a back that houses the stepper motor that runs the auger. And then at the bottom of that, there's a little electronics enclosure that houses the microcontroller. And I don't want to take that out because that's bolted into place right now because I forgot to take off those bolts. So all things considered, this is easiest to model as the separate parts that you would actually use to build it. So 1, 2, 3, 4, 5, 6 different parts. You could, of course, model the whole thing in one go as one part, but it doesn't make sense to do that. It makes sense to model them as separate parts and put them together into an assembly. The way this looks on SolidWorks is like this. There are separate parts that are combined together. The logic of the sketch relations applying to features is the same for part relations applying to assemblies. The difference is in name. Instead of applying relations, you now apply mates. So assemblies are made up of parts that are mated together, and different types of mates combine parts in different ways. So in this assembly, I can mate together the different parts, and as a result of having them all together, I could, for example, show my design to other people. I could visualize how it's going to look all at once. I could generate some nice images for use in documentation. I could actually see the whole thing in one go. And better yet, I can actually have the parts reference other parts. So for example, this part back here that houses the stepper motor, and this part here that houses the tube that the auger runs in, those are a total length that is just slightly shorter than the width between the walls on that shell, the chassis, if you will. But I could do the math every time, and in the event that I got a different food container, I can resize the nexus, I could have the tube resized manually, or I could just tell Solidworks, hey, this distance is maintained by the size of the stepper motor. That can't change. But this distance, that can totally change in the event that you have a different width between these two walls. That distance can get shorter or longer, and Solidworks is able to reference other parts from that distance as well. So I can have this top funnel feed down into that tube regardless of where this hole is. It would handle the geometry to figure out where it has to move around to maintain the relationship. Does that logic make any sort of sense? I'm sorry, are you having trouble hearing me?
No.
You just did this motion?
Sorry, I sneezed and you didn't say bless you.
I see. That's understandable. Well, they say sneezes come in threes, so I think you got 2 more this class.
I had 3 in the last class, so I think it went right.
Always the tone of surprise. Guys say I'm right as though it's astonishing news. So we could jump into this assembly in one fell swoop. But let's back off a second. Let's try mating together some different things, shall we? Something a little bit more easy. Unfortunately, to model an assembly, we have to have parts. So let's make a couple of parts. Let's say, for the purposes of this in-class example, we wanted to make, I don't know, like a 6-inch cube. And then on top of that 6-inch cube, we wanted to make a pyramid that was equilateral triangles like we modeled in class in day 1. So I'm going to make 2 parts. One is a cube, and one is a pyramid shape. And I'm going to establish a 6-inch dimension. Nope, not in. Let's try that again. 6 inches. Much more better. Extruded 6 inches in the mid plane. Boom, we have a cube. So I will save that on the desktop for now as cube. So we have a part. It's saved, and now it's gone. Now we can model a pyramid shape. I will start with the same shape we had earlier. I will model a cube and then remove material to get to the pyramid shape that we wanted. So 6 inches again. And then extrude it up. And just for funsies, instead of making this a mid-plane extrusion, let's make that a regular linear offset extrusion. And then I will draw on the front a nice equilateral triangle. Something like this. I will tell Solidworks I want these all to be equal lengths. I will cut through everything in both directions on the opposite side. And then, because we are getting real good at patterns, I'm going to not draw the triangle again. I'm going to establish an axis and then a circular pattern with the cut and the axis to 25. That looks cool. I will give you that, SolidWorks. I want 2 of them. I don't want them equally spaced. I want them 90 degrees offset. Yes, 90 units. Thank you. Okay, we made a pyramid shape. So I will save that again. I will switch to the isometric view first because that is a good best practice to develop in your muscle memory when you can. See how this thumbnail is obviously a cube because I switched it into an isometric view before I saved it. When I save the pyramid, it's also going to be using whatever the current view is when it generates the thumbnail. And if I make it all isometric, then we have a beautiful list of thumbnails from which to peruse to select out parts while we're making our assembly. Pyramid is what I'm trying to type. And gone forever. Now, let's go up to File New, and for the first time together here, let's click on the Assembly button. When you create an assembly, the first thing it's going to prompt you for is, hey, you probably want parts or other assemblies in your assembly. Which one would you like to start with? Just like in sketches, whenever you apply your first dimension, SolidWorks changes the geometry of the sketch to maintain that scale. Same is true of assemblies. Your first part that you import is going to be the part around which SolidWorks tries to frame everything else. So in this case, if I import the cube first, which I did by just selecting the cube, I'm going to get the opportunity to click. And wherever I click, the cube will be. Are you ready? Maybe like here. The cube is now there. Here is a term that doesn't seem to make much sense to this assembly right now, right? Because there's nothing else with which to have any sort of reference for what a position is. So the cube can't move. It is fixed in place. You'll notice that there's an F over here next to cube. That's not to pay respects. That's in fact to hold it in a fixed position. The cube is now fixed, even though it hasn't been maintained in any sort of relationship or mate. So the easiest way to get a handle on what that means is if you highlight over the cardinal planes. See how these are kind of off in space arbitrarily? Just like when you're making parts, you want your origin of your assembly to be placed somewhere intentionally, right? So right now, the origin is out over here, and it's fixed there, but there's a better way. I, for example, would like my cube to be positioned in such a way that the origin of the cube and the origin of the assembly are on top of one another. Or if I wanted to, I could also position the cube so that the origin of the assembly was in the bottom center of the cube, or what have you. So I'm going to first unfix the cube. Unfixing things is my specialty. If I right-click on the cube, the opposite of fix is float. When something is float, I can click it, and I can move it around. I can place it somewhere else. I could right-click, fix it again, but I don't want to do that. Instead, I want to mate the cube's cardinal planes to the assembly's cardinal planes. So what I'm going to do here is go up to the Assembly tab. I'm going to click on Mate. It's this thing that looks like a paperclip. That paperclip allows me to join things together. So I get the opportunity to apply different types of mates, and SolidWorks will try to select a mate based on what it thinks I want. So like right now, even though I don't have a mate selected, I can just click on Front. I can click on Front. It'll say, oh, you have two planes. I bet you want them to be coincident, don't you? Coincident here is a fancy word for touching. That's fine. I can make them coincident. So I don't know if you noticed, but the cube moved just a little bit to make sure that the front plane and the front plane were actually aligned. Similarly, I can mate together the right plane and the right plane, and the top plane and the, nope, come on, SolidWorks, potato, keep up with me. Right plane and right plane. SolidWorks, man, that's inconvenient. Why are you like the way you are? Okay, right plane, you guys saw it, it worked. I clicked the green check mark, and then I waited before I started clicking on other stuff. Potato's got to catch up. Okay, top plane and top plane. I now have applied three mates. I have mated together the front plane of the part with the front plane of the assembly, the right plane of the part with the right plane of the assembly, and the top plane of the part to the top plane of the assembly. So even though it doesn't look like I changed anything, the cube is now fully defined in space, and it can't move. And as far as we can tell, the infinite white void seems to be unaffected by the cube's position. The difference is now the origin of the assembly is in the center of the cube, which I like. The placement of the assembly's origin is going to become more important the more complex your assemblies are. It's also especially important if you're making a sub-assembly to insert into another assembly. I think that'll make more sense with more practice. Next, we can add in the pyramid and mate that to the top of the cube. If I want to insert a component, the button that I click is Insert Components. Like earlier, it'll prompt me to select a part. I'm going to select the pyramid that we drew earlier. I'm going to click Open, and like earlier, I'm going to click somewhere, and at that point, the pyramid will be located in that position. But since it is not the first part, its position is not fixed. I can grab it, and I can move it. Not only can I move it, I like to move it. I would go as far as to say, I like to move it. So you'll notice, as I drag this around, I could probably get pretty close to the top of the cube. I mean, all it would take is like an infinite number of these little micro adjustments. I could swivel around, drag a little bit more, and that looks like it's pretty close. But pretty close is not good enough for our purposes. We want it to actually be mated to the top of the cube. So just like earlier, we go up to the mate button, and we are going to mate stuff together. We have lots of options. Are you ready for some of the options?
Yes.
One of the options would be to click the bottom of the pyramid and click the top of the cube. SolidWorks will say, hey, do you want those two things to be coincident? I say, well done, SolidWorks. I could then click on one of the end lines, that is the line that makes up the edge of the pyramid, and then click on one of the edges of the cube. That would mate those together as well. And then I could click on a different edge and a different edge, and SolidWorks will mate those together. At that point, as a result of mating the bottom and two of the edges, I have fully defined the position of the pyramid. In the event that I change my mind, I can edit the mates that I created by opening up the hierarchy, clicking on the drop-down arrow next to mates, and I can edit these. Like, for example, I could delete these two, and now I'm back to just having one mate. I can click and drag this pyramid over here, and its position, though this plane is touching this plane, is not fully defined. So let's try a different way of mating it together. I could mate, say, the front plane and the front plane together. That would be a perfectly valid option. I could mate the right plane and the right plane together, and that would be a perfectly valid option. The only real advantage to doing it in these two ways is that by mating the cardinal planes together, if something changes, something else will be what I want it to be. So like if I change the size of the cube, if my mates were positioned relative to the edges of the pyramid and the edges of the cube, then if the cube got bigger, the pyramid would shift over and be like in the cube corner and not the cube center. Whereas now, it would be in the center. Does that make sense? Let's try it, shall we? In the event that I want to change my part, I can open up the part again. Like I could go modify the part and then hit save, and SolidWorks would be like, hey, your part was modified. Do you want to regenerate? And I would say, yes, SolidWorks. I can also edit parts directly in the assembly interface. So if I right-click on the cube and I hit edit part, it'll say, do you want to save? And I'll say, of course I want to save. Cube pyramid thing, question mark. Now that I've saved my file, it goes into the edit interface, and what I have right now is the same exact set of tools that I would have if I was editing the part just by itself as a part file. I have the same options here at the top again. The only difference is that now I can see the pyramid, and depending on how I have my transparency settings set in the performance button under the options that we talked about on day one, this might appear as like fancy shaded plastic. It might appear as like semi-transparent. It'll be a little bit translucent, a little bit opaque. Right now it's just dashed lines, and that's fine because potato. So if I were to edit this sketch, like maybe make it, oh, I don't know, 7 inches instead of 6 inches, and then hit exit sketch, SolidWorks will regenerate that part and then regenerate the assembly. So because I positioned the pyramid by mating its cardinal planes to the cardinal planes of the cube and then the bottom of the pyramid to the top of the cube, it actually stays centered. Does that logic make any sense? Do you have any questions so far?
Is there a way to make the triangle bigger with the cube?
Technically, yes. If you wanted them to be linked together,
Yeah.
you could do that. It's a little bit outside the scope of what I'm talking about right now, so don't get too intimidated by this process, but you can edit parts to reference other parts. So like in this first cube that I used to generate the beginnings of the pyramid, I can edit this sketch within the context of this assembly, and I can have it reference the other geometry in the assembly. Like for example, if I said this line and this line should be collinear, it's resizing that square to be the same size as the top of the cube. And then, because my equilateral triangles were generated relative to the actual corners of the cube, it will actually follow the geometry of the cube below it. So like, if the cube size were changed from 7 inches to, let's say, like 3 inches now, everything will repopulate properly. The reason this isn't a cube, by the way, is because when I created that first extrusion, I had just manually typed in 6. Does that answer your question? Do you have other questions? Again, again, I think it's the sort of thing that you get good at by practicing it. So practice a lot. Yeah.
Can you make it so that it's a cube all the time too?
Yeah.
Is that kind of hard?
It's not hard. It's just introducing a whole like subset of stuff that I don't really want us to talk about yet because I think it'll derail us too much. You can define global variables in SolidWorks. So we could define a global variable as like the size of the cube and then use that variable for the width of the sketch and the length of the extrusion. But I don't want to get into that. We are slowly progressing through stuff. If you want to know how to do that, talk to me sometime out of class. Or Google it. You kids know how to do that these days. Other questions? Okay. What I would like to do next is consider a slightly more specific example. If you guys go into D2L under Content and in-class resources, you have Piston. It's a zip file containing a bunch of SolidWorks parts. What I'm about to do now is attempt to assemble those parts together. If you would like to follow along, you're going to have to download that zip file. So here I go, downloading the zip file. And then I'm going to put that on the desktop. I'm going to right-click, extract it into a directory, and poof, I have 4 parts. One of them is a connecting rod, one of them is a crankshaft, one of them is a pin, one of them is a piston. If I wanted to assemble those together, I would start by creating an assembly. And then I would insert one of the parts. In this case, it doesn't really matter which one I position first because I'm going to be breaking the fixed relation anyway. So instead of positioning just one, we can just highlight all 4 of them and say insert all 4. It's fine, SolidWorks, we'll figure it out, it'll be good. So if I highlight all 4 of them and I hit open, SolidWorks will say, okay, where would you like me to place the connecting arm? And I say right here, perfect. Then it says, what about the crankshaft? You guys will notice, by the way, you can probably figure out what order I modeled these parts in. I got lazier as time went on. So we have 4 parts. We have a crank arm, we have a piston, we have a pin, and we have a totally accurate crankshaft. So what I want to do right now is model an assembly such that the mates in the actual world correspond to the mates in the parts. So I want this to be fully defined except for the rotation of the crankshaft. I want to be able to rotate that crankshaft and observe the piston actually moving up and down like it should. Does that logic make sense? So the first thing that I'm going to do is I'm just going to arbitrarily place the crankshaft, and then I'm going to right-click and fix it. So it's now fully defined. So I'm next going to mate together this connecting arm to the crankshaft. So to do that, I'm going to try to mate together the outside surface of this cylinder on the crankshaft to the inside surface of this cylinder on the connecting arm. SolidWorks says, hey, do you want those to be concentric circles? I say, you're spot on, SolidWorks. So now I've got the connecting arm positioned so that it actually goes around this cylinder. That's good because that's what I want, but its front to back position hasn't yet been fully defined. And remember that right now I need to position that position relative to the crankshaft, not relative to the assembly itself. So I have a couple of options, as you can probably imagine, when I go to do that. One of them would be to mate together the front plane of the connecting rod to, say, the right plane of the crankshaft. You'll notice that this is a right plane and this is a front plane. Doesn't matter for the purposes of mating them together, but it just means that when we reference them, we have to bear in mind that the person who modeled the different parts may not have placed the origin in the same sort of consistent way. So I could mate together the front plane of the connecting rod to the right plane of the crank arm. SolidWorks will guess that I want those to be concentric, and I do. And now its position is actually constrained front to back. However, if the person who modeled the crankshaft had positioned it such that the origin was like over here, for example, that same mate that we just did wouldn't work. Another way to accomplish what I just did would be to use a mate like, say, the symmetric mate. The symmetric mate takes 3 planes. it'll position one plane in between two other planes. So I could say I want this plane of the connecting rod to be symmetric within this face and this face. And that would accomplish what I want. I could also use the width mate, which is like the symmetric mate, except it uses 4 planes. It takes 2 planes and positions them in the center of 2 other planes. That sort of mate is really useful for very specific circumstances. Like, for those of you watching on the VOD, I'm drawing on the board. Just imagine in your mind a very accurate and detailed drawing. So if you were trying to make together, like, some sort of metal flange that was going to go into some sort of receiving joint on something else, like for the purposes of this class, you could imagine it's plywood. Like you want to make a dado in a piece of plywood that accepts another piece of plywood. Well, if you make this height the exact same as this height, in reality, there's no way it would actually go in, especially if it's a metal. So in engineering, we always have to establish tolerances. So what you would probably do is make this distance here like 1/8 of an inch or 1/16 of an inch shorter than this distance here. When you're mating those together, you can't say, take this plane and make it coincident to this plane, because then it's not centered, it's on the top. And you can't say, make this coincident to that, because then it would be on the bottom. And if you had other relationships in the rest of your assembly, those would be broken as a result. You need it to actually be centered. So if you use the width mate, you would say, take these 2 planes and position them in the center of these 2 planes. Does that logic make sense? So we can take like the front and back of the connecting rod and make those width mated to like the front and back of the crankshaft. Again, kind of outside the scope of what we're doing here, but you could do that. Anyway, now that I have the front to back position of the connecting rod established, let's study the position of the crankshaft a little bit more. So when I have that mated to my assembly, I want it to be able to spin, but I don't want it to move front or back, and I don't want it to be able to move right or left. So if I go into that part and I start looking at my ways to mate that, one of my options would be to try to mate that to the front of the assembly. So I take the front plane of the assembly and mate that to the right plane of the connecting rod. Now its front to back position is fully defined, but its left to right position isn't. And because I want it to be able to spin, I can't just take the left plane, the front plane, because that's the side plane of the assembly, and mate it to the right plane of the connecting rod. Because if I mated these 2 planes together, you wouldn't be able to spin. So instead, I could mate the origin to those planes. I could say, hey, origin, the origin of the crankshaft should be mated to the right plane and also the top plane of the assembly. If I do that, then Solidworks will ensure that the origin, which happens to be right here in the crankshaft, is always touching the right and top plane. So it's allowed to spin, but it isn't allowed to move. The only reason that works is because whoever modeled that, this guy, put the origin in the center of that tube. You have to place your origins intentionally, and usually that's informed by what you're going to do in the future with it. We also could have gotten away with like making an axis down that tube and then mating the axis to the front plane and then the top plane. That would have worked just fine. Anyway, now our crankshaft is able to rotate and our connecting rod stays attached to it. That's good. Let's keep going, shall we? Let's mate the pin to the top of the connecting rod. I'm going to use the concentric mate first, and then I want the front to back position of that pin to be positioned relative to the connecting rod such that it's actually centered. So this might be a good application for my fancy new symmetric mate. So if I go into the pin, I can see that it has a front plane that is in the center of the pin. So I'm going to use that front plane as the plane to be symmetric within this face and this face. Does that make sense? Again, I could have just mated the planes together. That would have been fine. I could have actually used the width relation too if there was actually a face on the end, and it looks like there's a little bit of a face on the end. Then I'll keep going. I'll say, go back to coincident. Hey, SolidWorks, make this tube here concentric around this tube here. Beautiful. And then I want to position that center again, and just for funsies here, I will actually use the width mate. So width mate, make these two planes centered within these two planes. And boom. So now, because I've fully defined the relative position, I'm sure that this will behave just like it actually does in real life. Look at that, guys. We have a totally realistic piston cylinder arrangement. That's beautiful. I like it. Of course that's wrong. It's wrong because the piston should actually be constrained left to right. It should only be able to go up and down. It should not be able to move around within the cylinder because it's actually maintained in position by the cylinder walls. So let's think about how we could do that. One way to do that, this is speeding up the process of talking through that because we only have 6 more minutes because I made a whole gear. I'm going to make the origin of that piston to the right and left plane of the assembly, just like I did on the crankshaft. So I'm going to take the right plane and position it to be concentric to it, and the front plane, is that actually, yeah, it is, and the origin. That'll constrain the center of the piston, so it can only go up and down. However, it doesn't constrain the ability of the piston to turn because it's a point in space. So to get that, I can mate the top plane of the piston to the top plane of the assembly, except instead of using a concentric mate, I can use a parallel mate. So now the piston can go up and down, but it can't go left to right or front to back. I realize that was fast. Do you have any questions? Okay. So the real advantage of this is that even though it isn't technically fully defined, it actually behaves like it would in real life. This is useful when you are modeling mechanical parts, which, spoiler warning, you're going to do a lot in your mechanical engineering degree. There are special mechanical mates to try to recreate the behavior of, say, gears with each other, or hinges or screws. You can position offsets, so you can be like, hey, I want this door to open to anything between 0 and 120 degrees, or I want this door to open until this point on the back of the door intersects this plane over here. Those are all things that you can do within the mechanical mates. So the assemblies don't necessarily have to be fully defined, but they can be. By the way, since we're talking about moving stuff in SolidWorks, when you guys take fundamentals of machine design, you're probably going to have to try to model a 4-bar linkage and then animate it. You're going to have the option of doing that mathematically in something like MATLAB, but if I were you, I think it's better practice to model that sort of thing in SolidWorks. So in the event that you want to generate an animation in SolidWorks, or actually a really fancy image, you can do that too. The animation is going to involve what's called a motion study. I'm not ever going to make you have to do this on homework in SolidWorks. I'm not going to make you do it on the project. This is outside the scope of this class, but it is kind of fun knowledge. In a motion study, we can animate motion and have it behave like it would relative to those constraints. So like, for example, I could tell SolidWorks gravity is down. Use the relative densities of these different parts to actually try to figure out how they would behave with gravity. Or I can say, apply a motor to this face. So if I apply a motor in the clockwise direction, and I tell SolidWorks I want it to rotate at like 100 RPM, that's maybe more like 60 RPM for now, because we're just generating a nice little animation of it going around. 60 RPM would give me, across a 5-second animation, we can change that, 8 frames per second. What is this, a PS4? So 60 would be a little bit more of a realistic number. Have it calculate through the different frames in the animation. And that was terrifying. So now we can actually play the animation.
This is peak performance.
Peak performance. Okay, stop it. You've got to no longer do that. So once you generate the animation, you can save that as a video. So like I could save this to the piston folder on the desktop as neat video! Exclamation mark. Can generate a video that is 1920 by 1080, because of course. And I want the output animation to be like 60 frames per second. Note, what it's doing is it's using the relative perspective of the camera that we're looking through right now as what it's using to generate the video. So you would actually want to position that to something that made sense, but for right now we're just demonstrating how it works. So I have the entire animation 60 frames per second. Okay, I'm going to make that 30 just so that hopefully it finishes before the end of class. I'm going to save the file. It's going to say how do you want to encode the video. You can just leave it default, it's fine. Okay. Now we are rendering video.
On a potato.
On a potato. Ironically, we are rendering a video and then we're encoding a video of the video being rendered and streaming it to YouTube. That's fun.
All on a potato.
All on a potato. Okay, so it took a minute to get you through 2 seconds. So another 3 seconds should take a little bit more than a minute. Okay. Before you guys get all ready to leave, I'm going to talk through the homework that's being assigned today, so bear that in mind. Okay, we have a 5-second video. Let's go look at it, guys. Oh, look, neat video. Hey, we made a video. We did it, guys. Well done, us. Speaking of things being done well, if you go into your Dropbox, you can see that Homework 5 is now available. Homework 5. Okay, hold on. It's not available, though. Stand by.
That's too bad.
Available on February 6th.
That's wrong. Okay, I'm going to go into teacher mode for a second. All powerful. Okay. Ultimate cosmic power. Itty bitty living space. Okay, and it's actually due next Tuesday. Okay, guys, guess what? If you go into the Dropbox, you can see that Homework 5 is available. And in Homework 5, you're going to be tasked to make another rocket. I know how much you guys love rockets. So this is Rocket 2. And in Rocket 2, you are making a rocket as a result of different parts. So you have to model a nose, you have to model a fuselage, you have to model a fin, and you have to model a nozzle. The part requirements are all laid out here. And then you have to mate them together like they actually would behave into one assembly. So you're modeling a fin, you're modeling a fuselage, you're modeling a nozzle, you're modeling a nose, you're putting them together into an assembly, and then you are generating JPEGs for all 5 of those files. So how many different files should you be submitting? You guys got this. Did you have a question?
Yeah. Is this due in 2 weeks?
This is due in a week. This is due next Tuesday.
Okay.
See you guys on Thursday. $30? Because I made it out of PETG. Because I wanted it to be food safe. Because, you know, I don't want to murder my cat. I think this works. Kilograms. With like a little half. So realistic, probably like $25. Before we start talking about that, I'm going to stop the live stream so our conversation isn't broadcasted to everyone.